So back to some regular equation types. In acidic solution, hydrogen peroxide, so that's the hydrogen peroxide, is oxidized to oxygen. Well, there's the 2 electrons on the right-hand side telling us that it's oxidized. There's the oxygen. And by potassium permanganate, so if hydrogen peroxide is oxidized, potassium permanganate must be reduced. So first thing they want is the half equation for the reduction of MnO4 minus ions to Mn2 plus ions in acidic solution. Now, my impression is that you do this so often that you're almost expected to have this memorized, but let's generate it anyway. So there's MnO4 minus going to Mn2 plus. The first thing to do is look at oxidation numbers. For the permanganate, the manganese must offset most of this negative from the O4. Oxygen is going to be -2. 4 -2 is -8. The whole thing's 1 minus, so that means the manganese must be +7. And of course over here, dead easy, 2 plus. So the manganese goes from 7 to 2. That is indeed a reduction, and it's a reduction by 5 electrons. So thus the reduction part, without balancing anything else, is the permanganate needs 5 electrons to turn the manganese to Mn2 plus. Now, of course, you look at this, and the first thing we see is, well, the charge is imbalanced. Well, that's okay. We know we're in acidic solution, so we have H pluses that we can use to balance the charge. Charge on the left-hand side, -6. Charge on the right-hand side, +2. So to get from -6 to +2, counted on your fingers, you need a total of 8. And because we're using H plus, we're going to put those 8 H pluses on the left-hand side to make the left-hand side more positive. So thus incorporating that into our half equation, the 8H plus on the left-hand side gives us this. Finally, we see we got 4 oxygens. We have 8 hydrogens. All we can do to balance this is incorporate water. And of course, water has hydrogen to oxygen in a nice 2-to-1 ratio, so that works. And we need 4 waters to give us 4 oxygens, or 4 waters to give us 8 hydrogens, however you want to think about it. So there's that half equation that, as I say, should be very familiar to you, almost to the point that you should be able to write it straight out. So using the answer in 1 and the half equation given, so that's the hydrogen peroxide, to deduce the overall equation for the reaction. Well, there's the reduction, there's the oxidation. In order to put these together, we have to multiply so that the electrons cancel out. Thought process to get that is to say, well, what's the lowest common multiple of 2 and 5? And lowest common multiple of 2 and 5 is 10. So how do we turn 5 into 10? We multiply it by 2, so that's multiplying the whole equation by 2. How do we turn 2 into 10? We multiply by 5, so that's multiplying the whole equation by 5. And when we do that, we get these. So look at the reduction one, you've multiplied everything by 2. Look at the oxidation one, you've multiplied everything by 5. Now when we put them together, the electrons will cancel out, and also some of the hydrogens will cancel out, because we got 16H plus on the left, 10H plus on the right. Cancel out what you can, and you're left with 6H plus on the left, and then the manganese terms not changed, the peroxide, still 5 of those, and then still 8 of the waters. So an important reaction generally, a yucky looking equation there with 2s and 5s and 8s and so forth, but what's really important, of course, was the permanganate half equation there combined with that one in order to give us the overall equation. So the ion electron half equation for the oxidation of ethene dioate ions is given below. Again, we've got an oxidation because the electrons are on the right-hand side. And write an equation for the reaction of acidified manganate 7. So if the ethane dioate is going to be oxidized, our manganate 7 or permanganate ions is going to be reduced. And of course, we know the equation for that, either because we've memorized it or because we generated it in the previous question. So we got permanganate going to Mn2 plus, that's reduction. There is our oxidation. Again, we want to get the number of electrons equal. So that's the least common multiple of 5 and 2, which is 10. As we did in the previous question, multiply then the reduction by 2 to get 10 electrons, multiply the oxidation by 5 to get 10 electrons, put them together, and you get that equation there. Okay, very, very similar, of course, to the last question. Even more similar was this one from 4 years later. Oxalic acid is the common name for ethane dioic acid. Found a wide range, blah, 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 made a dihydrate. Now, look at the difference, though, between our oxalic acid, which we're going to write as COOH twice, right, and our oxalate, which is just the same thing, right, ethane dioate, minus the hydrogen. So essentially, this is exactly the same question, question 21, as question 20 4 years before. You oxidize this, you get 2 CO2 and 2 electrons. The only difference is here you've got the H pluses floating around, here you don't have those H pluses floating around. So therefore, all we have to do is pretty much do exactly what we did the last time, but instead of having oxalate in there, we're going to have 5 of those, and put all this together again. Going to be exactly the same idea. Again, a little bit of a difference in terms of the H pluses. We start with 16 H pluses with the permanganate. We got 10 H pluses as the products here, but otherwise exactly the same question. So obviously the examiners like ethane dioate or ethane dioic acid or oxalic acid and oxalate if you're using the old way to name things. Another one that they really want you to memorize, diagram below shows some of the reactions of potassium iodide solution. The potassium is just always going to be a spectator ion, doesn't matter. The iodide is what is important here. So we're taking iodide, reacting it with Cu2+, and we make a solid B and a brown solution C. So this is one that, again, apparently you should just recognize. We expect ordinarily the copper 2+ would react with the iodide and make copper iodide, but that's soluble, so that would just float around in aqueous solution. However, copper 2+ doesn't half mind being reduced to copper 1+, and iodide can relatively easily be oxidized to iodine. So the reduction would be copper 2+ plus an electron going to copper plus. The oxidation to iodides going to iodine plus 2 electrons. And so therefore put all these together and the reduction goes on, making Cu+. When Cu+ bumps into iodide, it makes the solid Cui. So therefore the solid Cui is going to be the precipitate. And then you've also turned some of these iodides, oxidize the iodides to iodine, so that is the brown solution, iodine water. Okay, so a nice little redox reaction going on instead of just a normal old copper 2+ plus iodide making the copper 2 iodide. There we go again, looking at feasibility and so on. Write an equation for the proposed reaction for this, looking at those two. Hydrogen peroxide can oxidize Cr3+ ions in acidic solution to make the dichromate. You might remember part of this from a previous part of this work through, but here all we're doing is writing an equation. So we're told for sure that the hydrogen peroxide is going to be reduced because we want to oxidize the Cr3+. So therefore make that the reduction. This is the oxidation. Looking at the number of electrons, because we want to balance those out, we got 2 electrons and 6 electrons. Lowest common multiple of 2 and 6 is 6. So all we got to do is multiply the reduction by 3 and leave the oxidation alone because that's already got the 6 electrons in there. Put all those together. Cancel out the electrons, cancel out some of the H pluses, cancel out some of the waters, and you're left with the much more palatable expression as to 2 Cr3 pluses, 3 peroxides. You only got 1 water left because while you had 7 on the left here, you have, when you multiply this by 3, 6 on the right, so those cancel out to leave you with 1 on the left. There's the Cr2O72 minus there, and again cancellation out for the H pluses. We had 14 H pluses on the right. From the reduction, 2 times 3 or 6 H pluses on the left, 6 on the left, 14 on the right, all balances out to 8 on the right. Some students were given a mixture made up of 50% each of sodium chloride, sodium iodide, and asked to design tests to show the presence and concentration of iodide ions in the mixture. One student decided to try electrolysis, dissolve some of the mixture in distilled water to give a concentrated solution, passed electricity through the solution using inert electrodes. The negative ions, so that's iodide and chloride, moved to the anode where maybe they lost electrons. State what was seen at the anode to confirm the presence of iodide ions. Okay, well, they gave us these electrode potentials, which are all oxidations here, because this is what's going on. If we at the anode is where oxidation occurs, losing electrons. So either we can oxidize iodide or we can oxidize chloride, because that's what we got there. Well, neither of those wishes to be oxidized. For iodide, it's only minus 0.54. Chloride is minus 1.36. So that means it's much easier using electrolysis to oxidize iodide. So that's the oxidation that's going to happen. And of course, it forms iodine. So therefore, what will happen is the negative ions, the iodide, move to the anode, lost the electrons, leaving iodine, which means you get an orange-brown color around the anode as you make the iodine.